Okay, welcome back. So let's continue our lecture. Before that, I would like to do some summary. Briefly make a recap for you. So last time we talked about can we find a state variables other than the internal energy, right? So which is entropy. So how can we get the entropy? We found that if we can apply by a integrating factor, and then it will make inexact differentiation exact. All right, and then we found that divide by p divided by t can be two good integrating factors. So we obtain the famous equations du equal to TdS minus PdV. And then we introduce Carnot cycle, which is an ideal cycle procedure, and including two isothermal process and also two adiabatic process. And then by using that, we can relate it to efficiency, because Carnot cycle is an ideal process, so it will make the equality become, I mean, the debug Q2 T2 plus debug Q1 over T1 equal to 0. And then if something become realistic, it become less efficient. So you will have a less or equal to 0, right? And then we talk about that the second law is that the S is a state variables as long as you have the same, I mean, it's not depending on path, right? So and also the system during the process will never decrease their entropy. All right, and this is, we stop there, and then we are going to proceed. All right, so the second law is that the entropy of part of system can deceive, I mean the part of the system. All right, however, the net, the overall entropy will always go up. So you can see that it is possible to decompose the change in entropy. You can see delta system, delta S for system, delta surrounding. So you can see that the delta S is the system itself. Itself, okay? And the delta S plant, the plant is actually surroundings itself. Okay, and the delta S, T is the entropy transfer. You see the transfer, T is transfer across the boundary between system and surrounding. So actually they have opposite side, opposite side sign. Okay, so they are either positive or negative to each other. So actually, when you sum them up together, universe, which means that overall net entropy, these two will cancel each other. So delta S system, delta surrounding, this one or that one, will always greater than 0. Okay, greater or equal to. Okay, so equal sign holds for a reversible process, or you can say perfectly ideal. All right, so that's it. 好，我们讲第二定律，就是说，其实叫什么熵啊，它就是会总熵永远都会是一直往上的哈。那我们当然可以把它分割开来看，例如说系统跟 外围的外围的环境，这两个加起来就会是 universe， 对吧？就是全部的意思。那当然，delta system 里面可以是说，它自己 delta S 自己的变化，然后还有 delta S plan surrounding 的变化。那 delta ST plan 是在这个边界上，就是 system 跟 surrounding 的边界上，他们自己会互相交换的 entropy。那通常不是就一定了哈，就是过去就已经过来的嘛哈，那只是不同的 sign 啊，不同的符号而已。那所以你加总起来，它们就会抵消掉，然后到最后 delta S 的 universe， 也就是说全部的 net entropy 熵的改变，就会是系统本身的改变跟 surrounding 周围环境本身的改变是相加的，所以实际上就是会大于等于。但你可以发现，因为它们是 different sign 嘛，所以它其实是在 delta system 跟 delta surrounding 它自己本身它可能是可以变小的但是总体来说它就是往上升的。Okay, so let's talk about entropy and available energy. Okay, this is quite. I mean, available energy actually related to efficiency. Because if the energy you can use, which means that you can use that as your performance, so your efficiency can go up. But because some energy is not available, so which will decrease your efficiency. All right. So you can see heat can be converted to mechanical work. Okay. So the bar Q eta, the eta is efficiency. Okay, we see that in page 6. Okay, the efficiency here. So you can see is page 6. Okay, and we also see that the eta equal to 1 plus Q1 over Q2, and then we also in page 6 we also know that 1 minus T1 over T2. All right, so this is what we obtained in the previous 4 pages, P.6, page 6. Okay, so which means that we can make the eta replaced by 1 minus T1 over T2. Okay, so you can make it here, right? And also we found that the heat can also be converted to mechanical work. As you can see that the heat inputs into the system can eventually make it work, make it do some work for other things, but no 100%, right? So you need to times eta efficiency to obtain your actual bar W, actual work you can done to the put down for the by the system. Okay, so the available energy, you can see that this is something that actually make it work. Okay, but which means that the bar Q T1 T2, because you suppose we want 100%, right? But 100%. But in the practical, in real world, you need to minus T1 over T2. So this T1 minus T2 is something unavailable. Maybe it become the heat, temperature, heat released. So the entropy always increase, no problem. The available energy always decrease in a irreversible cycle. So you see that energy will always become unavailable each time, each cycle. Okay, so yeah, that's it. So you can see that it will make more difficult, make the energy more difficult to be used. Okay, so you will always find that there will be heat in your car engine. Ideally, we don't want this heat. I want this heat go back to make it work, right? Make the car pushing further, right? But it still converts into more difficult energy that can be used. So yeah, so that's why we are going to trying to invent certain material like thermoelectric material that can convert heat to mechanics or electric power or something. So yeah, this is important, and then that's why you are here to study material science engineering, right? All right. So, and also another thing is that entropy is a measurement of randomness of the internal motion. 大家都一直迟到，那这样子，我就，他每次都这样。他很好笑，他每次都会消失，这是一个 bug， 它会消失不见。哦，有了 ，OK， 下次要准时 ，OK， 应该说提早了啊，我会准时，所以要提早。All right， 如果你要线上话 ，OK， 好。So entropy is a measurement of randomness, internal motion. So you can imagine that you have particles, right? And your particle, if you put it into the container, and then it will, freely expand, and then you will find that it will always go into random part, right? Random situation. So which means that you are more difficult to use that to manipulate, to control all the internal motion of the particles or molecules. So which means that the entropy, randomness increase the entropy and also increase something that you can control and something that you want to use that as the work or something. So it will more kind of more difficult to more unavailable energy. OK， 好，那我就说熵跟可以用的 energy 是有相关性的。那我们可以看到它其实是可以，热是其实是我们把系统让它做功的主要来源，对不对？但是不可能把100%的热都转换成功，一定会有某一些效率问题。那效率的表示是在第6页就写过了哈，所以我们就发现我们把它写出来以后，我们就会看到就是不可以用的是这样子的温度，不是这样子不可以用的温度哈，不可以用的底坝 Q T1 T2 好，那这是它不可以用的。那也就是说，它就是会把热，就是在做功的时候，就会有一些能量会用成，就会被转换成我们用不到，我们无法使用，越来越难用的，越来越难用的一个的能量例如说废热，废热就比较难用，那电我们就很容易用嘛，对不对哈？那所以说，那它总是会有一些就是变成无法控制。那这个无法控制，其实就是这个能量转换成，例如说热的话，其实你看它不就是它的，例如说气体，它的能量已经变成分子的，就是动能。那这一份的动能其实就是让这个变成越来越 random， 越来越随机，你就越来越难用大概是这样的意思。好。All right, so let's see another possibility. Okay, so can we combine the first and second law by using some mathematic or some knowledge we introduced previously? So let's take a look. For a reversible process, du equal to d bar qr minus d bar wr. Okay, and tdspdd. No problem. Okay, so this is what we learned previous few pages. And we noticed that we always mention this should be a reversible process. Okay, so you can see QR, WR. Okay, and yeah, and TDS minus VDB. So in the previous few pages, we introduced this based on the assumption reversible process. But we are going to know that if this is possible to take out the reversal process, can we make it general? Is that this explanation so limited to reversal process. Can we combine them into first and second law? Can we do that? Let's take a look. We know this information at in the page P4. Okay, so let's combine the review 1. Page 3. We introduced that the first law, which is general, not only for reversible, it's general. du equal to d bar q minus dw. No problem, right? And then, oh yeah, we should write down this is equation 1. du equal to d bar qr minus d bar wr is equation 1. And the second one is this. And then we want to see the second law. Second law has TDS equal to d bar QR greater than d bar Q, and which is based on page 7 in this PDF. Okay, and then we can further to make this TDS things become equal to d bar Q plus epsilon. Okay, what is epsilon? You see, d bar QR is greater than d bar Q. All right. So if we want to make it equal, we're just adding something. Okay, epsilon. So it will make equal. Okay, and the epsilon, of course, it can be defined as dissipated work. D bar QR means reversible, right? But D bar Q is non-reversible, which means you definitely missed something. You definitely lost some energy. So this is something you lost. And this is we call, equation 3. All right, so I want to emphasize a little bit, make it d bar Q, d bar Q. Okay, I just want to make it highlight, and then you will correlate them later. So you have equation 1, 2, 3, and then if we substitute 1 to 2, right? If we substitute 1 to 3 to 1, 3 to 1. If we substitute 3 to 1, all right, we can obtain du equal to d bar q plus epsilon minus d bar w r. Yeah, no problem, right? And we name it equation 4. Okay. And you see that this one is and you notice that because the d bar q r become d bar q plus epsilon, you introduce d bar q. The d bar q is irreversible now. Irreversible now, right? It becomes irreversible because, I mean, you introduce the relationship between d bar qr and d bar q. Okay, so you take the relationship, you connect them together in this equation 4. So let's substitute or compare. Let's compare 4 and 2 equation. Okay, you see 4 and 2. What's the difference? We know that, okay, d bar w equal to d bar w r minus epsilon. And we say this is equation 5. And typically we know that dissipated work appears as heat. This is a very typical example, and the heat typically is difficult to use in the real world. So we can say this is unavailable energy. Of course, we can inventing something like a thermoelectric material to make it available again, but still it is some dissipated work appears heat all the time. Okay, so after we compare, we draw dW. We find that dW here. All right, so then we found that this equation can eventually write down as d bar Q minus d bar W. Okay, you summarize everything above. You can say, okay, d bar Q equal to d bar Q bar minus epsilon. Good. And d bar W is d bar WR minus epsilon. And there's a minus sign. So you can see here is equation 3. Here is equation 5. And you notice that they can be canceled. Right? So eventually, no matter you considering reversible or irreversible, either way, you can obtain the same. You have the same form. All right. But one thing we are going to say that although it can obtain the same equation, but can you say TdS equal to d bar Q? Can you say minus PdV equal to d bar W? No, we cannot. We can only say, yes, when they combine together, you can still have du equal to TdS minus PdV because that minus epsilon, minus epsilon and minus epsilon will cancel each other. So that's the reason why this one still work. But individually, they are not equal. All right, so you need to be careful. So I will say individually not equal. All right, so you need to be careful. 好，那我们要讲就是我们要结合第一跟第二定理。好，那我们在第4页的时候提到，就是说哦，du 是 for reversible 的，是可以回复的，然后它可以写成 TdS 减 PdV，然后当然我们知道 TdS 会是 d bar QR，PdS minus PdV 就是 minus d bar WR， 好，有 R 后要小心，我们说它是 equation 1。那第一原理我们在 Review 1的第3页有写出它是这样子，没有问题。那我们把红色标成热 W 标成蓝色。那第7这个 PDF 第7页我们又说 OK 底 bar QR 会大于底 bar Q，no problem。好，那既然它大于，它一定是可以写成等于，再让右边的加上某个东西，那某个东西一定就是它消耗的能量，它是无法被使用的，例如说废热之类的，好，废热之类的。好，那既然这样，我就把它带回第1个式子 ，OK， 我们就发现它长这样子。那这时候我们再把这个式子跟第2个式子，就是第二个式子，不对，我们把这个式子跟第2个式子比较一下。不要忘了，这个式子是 general 的，它是不管是 reversible 还是 irreversible 都可以哦。所以他把这两个比较下来，就发现，d bar W 其实就是 d bar WR 减 epsilon 嘛。 也蛮合理的嘛哈。好，那这时候我们再把这全部就是加总起来，我们就把蓝色跟红色加总起来，我们就会发现，其实写成这样子以后，它是可以消掉的，也就是 dissipative work 这个项是可以消掉的，所以我们终究还是可以得到 du 等于 TdS 减 PdV 是 for 一般性的，它是完全可以，不管是 reversible 还是 irreversible 都可以使用的。但是要注意的一点就是 TdS 不会等于底坝 Q 哦 ，P minus PdV 不会等于 minus d 坝 W 哦，这要小心，因为你知道 TdS 实际上是等于底坝 Q 啊，你知道 minus PdV 实际上等于 minus 底坝 WR， 好，只是刚好我们的 epsilon 会互相消掉而已啊，就是这样。All right, so let's continue. I kind of remind you internal energy U and enthalpy H, which is related to, I mean, this page is actually, we taught that, we introduced that like last time, right? I mean, yeah, last time, in the beginning of last time, right? So, okay, so we remember this equation is actually, I guess you remember with the, okay, which is the pink highlight before, and then we substitute the bar Q into internal energy and enthalpy, and then we also know that du equal to CV dt, and we also know that the H equal to CT dt. Okay, so all these things we have introduced in the last page, last PDF, okay, last time. So I just want you to, I just remind you what is this. 这一页我们之前上个礼拜的一开头有讲过，对不对？哈，还记得这个红色的区域吗？粉红色的区域。好，那这些纯粹只是提醒你，好，就是不要忘了这个式子啊，也不要忘了就是把底坝 Q 带进去，底坝 Q 带进去，你会得到就是 du 等于 CB dt， 好，然后 dH 等于 CP dt， 因为等一下我们会用到这个东西，好，所以这边就是让记忆恢复一下记忆了哈。All right, so after you kind of recover your memories about the internal energy U and enthalpy H, we were going to summarize entropy change in processes. What we have done here is actually similar to we kind of summary for work. Remember that? 还记得我们之前有做过，把功就是每个不同的就是 process 的功都把它算出来嘛，然后整理成一张PDF 上面嘛，这要做一模一样的事情。So we are going to do exactly the same thing like last time. We summarize all the work change in different processes. Here we do the same. All right. So let's continue. Our dbar QR equal to T du plus PdB, no problem. And then we can write down the ds by dividing integrating factor, right? So dbar QR, we do the dividing temperature. So we can get the equation 1 here. Okay. Then we're using equation 1, and then we can continue to apply to different process. Okay. For example, the first one is adiabatic process. Yeah. 你知道，不好意思啊，我现在一直被我的手机在震动，吱吱吱吱，为什么呢？因为我有个，我不知道大家有没有听过许家伟同学，就是之前有一个学长，然后他是我的学生，然后他应该算是也可以算是我的老师了。为什么？因为他那时候在我的实验室，然后他想说要做 AI，然后我那时候也不会 AI，大概2017年左右，然后我也不会 AI，我就想说哦你要学我就跟你一起学啊，好我们就开始学 AI。 然后 AI 到后来他就很厉害，他自学，然后跟我一起讨论，那我们就做出一些好成果。然后他现在在 MIT 啊，他 MIT 他是我们系上第一个拿到全额奖学金博士 MIT 的人，哈哈，系上有史以来啊，太棒了，与有荣焉。好，然后他就去了，然后当然我就没有管他了哈，他那边有更好的老师在指导他吧，哈，世界级的。然后结果为什么那手机在响呢？吱吱吱，因为他得到 Nature 了，Nature 的第一作者呢，哇，就是在这几天的事情。然后我觉得他好帅哦，Nature 呀，我自己都没有发过 Nature 啊，我也很想要发 Nature。当然啦，我有帮助过一些人，就是我有帮助过一些其他老师做一些模拟，让他们的工作可以到 Nature 上，但是一直都不是我，就是我都没办法用自己的名义去发一篇 Nature，所以哇，Nature 真的很难。然后他现在得到第一作者的，然后 Nature，我觉得真的是了不起啊，真的是与有荣焉。然后我的那个手机就一直大家在讨论这件事情。好，不好意思。Okay, let's continue. I just saying discussing my previous student Jia Weixu, who is a really talented, gifted student, and now he's in MIT as a PhD student with all the scholarships, which is the first in our department history. And he now got his paper as a first author, got accepted by, wow, it's nature itself rather than nature something. Okay, it's nature. This is the most difficult nature journals that we can publish. Wow, difficult. Proud of him. All right, that's it. Let's continue. Uh, so we need to apply the DS equation 1 into a diabatic process. All right, so you see, a diabatic process means that the bar QI equal to 0, no problem. So make this one 0. So ds equal to 0. So s equal to constant. So which means that a reversible adiabatic process is an isentropic process. Well, which means that there's no s change. Isentropic means s equal to constant. Simply as that. Okay. If this is isothermal process, which means that there's no temperature change. So you can just directly substitute whatever the temperature is. So your temperature is always, it's fixed. So easy. You just do the integration for that, and then you can get S2 minus S1 equal to the integration because everything is fixed. Okay, so like nothing. All right, so it's P7. We also mentioned that S2 minus S1 equal to Q over T. And if something is isothermal, isobaric change of the phase. Okay, remember that what is the isothermal and the isobaric change? Remember that? It is the isotherm with the platform, right? Platform is an isobaric. It's a pressure constant. Also along the isotherm line. So your debug Q is the heat required for phase change. What's that? Latent heat. Okay, latent heat. So we just substitute this by latent heat. Done. Okay. Another interesting thing is that if the material under isochoric process, of course, this is reversible. which means that isochoric means V is constant, right? And because V is constant, so your U, naturally you can say this is a function of V and T. And because V is constant, so it's actually U is function of T only. So you can say 1 with dV equal to 0. You see, 1 dV equal to 0. So your ds equal to du over T. So du over T. So this is du over T. What is du over T? Du over T is actually related to CV, right? We mentioned that previously, right? This one. Remember that? Okay, we will use that later. Okay, so that's the reason why I recall that page in front of before this 13, page 13. Okay, now after this, we can S2 minus S1. Entropy change can be just CV dt over T. Okay, and don't you think this is similar to an ideal gas behavior, right? Because you know ideal gas behavior is the function of T only. And if anything material undergo reversible process and also isochoric process, its behavior is similar to ideal gas. And its entropy change is just based on the integration of CB over T. Yeah, that's it. 好，我们不是有讲过，就是 work 之前我们有做一张表嘛，哈 ，work 怎么样改变在不同的 process 状态下，这边也是一样，我们要做 entropy change 这个整理啊。那在不同的 process 状况下，当然啦，我们当然假设 reversible 比较容易计算嘛，哈。好，那我们就把这个式子写下来了，然后就把这个式子应用在不同的状况下。那 diabatic 就是没有热嘛，没有热的话那这边就等于0。ds 等于0的话，就是 s 就会是不变的。那所以也可以直接讲，就是说，如果今天它是 reversible 加上adiabatic 的话，它其实叫做那什么 entropy 是不会变的 process， 叫做 isentropic。OK， 那只是一个名字而已。好，接下来 isothermal process 也是很简单，因为它 T 就是变成常数，不会变嘛，哈，它就是直接拿到符号外面很简单。接下来这个 isothermal and isobaric change 的话，它是记得吗 ？isobaric 跟 isothermal 就是在等温线上的那个平台，它会同时等温、同时等压，以及就是给相转变嘛，那相转变的热的交换就是 latent heat， 那其实就把它写下来就对啦。那接下来 isochoric process 的意思就是说，在这样的状况下，你是0的 ，dB 等于0dB 等于0，那你的 ds 会等于 du 除以 t du 除以 t 的话呢，那我们就发现 du 跟 t 有什么关系啊？那就是 cv dt 嘛而且另外一件事情是，你看到这个式子，它不会，它原本是跟 s 有关系的，但是现在 dv 又不会变了，所以它也不会跟 v 有关系。那所以你的 u 不就是跟只有 t 有关系吗？那不就是代表说这个系统跟 ideal gas 像吗？因为 ideal gas 也是只有对温度是它的函式嘛，那所以说这还会有一样类似的表现，所以它的 du 就会等于 cv dt， 然后它们的 entropy 的改变就会直接做它的积分。OK， 那这也是为什么我在前页要把刚刚的那个 ideal gas 之前的这两个表给大家复习一下。Next, continue. We're still using this. Okay, we're still using this, and then we notice that Now, we're still saying that this is equation 1, all right? Because we cannot make it compact in the one page, okay? This is the second page. Continue the content, okay? And so now, for isobaric process only, as you see, isobaric process, which means that it will related to CP, right? Previous one, we related to CV. Here, isobaric. Of course, you need to use the heat capacity measured at constant T. And what is it related to CP? H, right? So again, review 1, P14. You have H equal to U plus PV. This is the definition of H. So the change of the H is du plus PdV plus VdT, dV dP. And this part, let's take a look. Do you think this is the bar QR? Okay, very similar. So yeah, so we can just make it very combine the combine equation 1 to these things, and then we notice that isobaric process. Isobaric process means dP equal to 0. Okay, so your H equal to H. Typically, we say that this is a function of temperature and pressure, right? H related to the temperature and pressure, and then now isobaric is not anymore. So you can say the dH equal to Cp dt. And then, of course, you know that this is mentioned in the previous page, right? And it is equal to the bar QR. So S2 minus S1 equal to 1 Cp. Okay, that's it. So you can compare this result with the previous one with the Cp over T dt the integration. All right. 好，接续前一页放不下了哈，一页放不下。那最后一个就是 isobaric， 就是等压的状态下的过程。那等压刚刚是 CV 嘛哈，在体积不变的状态下，这是现在是等压的状态下。等压状态下刚刚是 CV， 现在就是一定是 CP 嘛，对不对哈？那什么东西跟 CP 有关 ？enthalpy 嘛，对不对哈？所以我们就看 enthalpy 的改变量。好，我们改变发现哦，这个前面的项就是我们的第一个式子嘛，哈，式子 1， 式子1，那我们就带入进去，就发现它会长这个样子。那就这个样子哈。好，那这个样子结束以后，我们就会发现 isobaric process 底 P 会等于0，就没了。所以哇，原来在 isobaric process 状态下，你的 entropy change 就会是，其实就是你的 Cp 除以 T 的积分。是这样而已 ，OK？ 那怎么来的？当然就是刚刚我们复习过的那一页，哦，黄色的荧光笔的那个部分。All right. Finally, we summarize all the entropy change in different type of reversible processes, and then we further narrow down. We adding one more condition for ideal gas. Previously, we're not saying that they are ideal gas, although they're really similar to ideal gas, but they are not. Okay, but now if we narrow down for the ideal gas, we can introduce two more conditions. The first one, du equal to Cv dt, of course. Okay, and Pv equal to RT. Where's n? Divided by v, capital V divided by m becomes small letter v. All right, so n including here. So if we has ideal gas assumption, we can introduce further two conditions, and also the U equal to CV dt. Now, why we yellow highlight? Because I mentioned that in the previous page. All right. Next. So again, I write down ds equal to d bar qr over t equal to du over t plus p over t dv. Yeah, don't you think this is equation 1? So this is equation 1. So basically what we do is exactly the same. Always do the same thing, but just keep adding different conditions to see what happens. All right. Okay. So based on this, we can further make it, well, du cv dt. So here we are. Okay. And then what we can do is we want to see the delta S, right? So we do integration for every turn. What will we do? And if CV is a constant, which means that, yeah, we meant to make it CV out of the integration symbol. So S2 minus S1 equals CV natural log T2 over T1 plus R natural log V2 over V1. Okay, so that's for ideal gas entropy change, the general formulation. So you can see that, okay, you can see that we always focus on change of entropy. That's because it's really difficult to determine the randomness of the material by using classical thermodynamics. Okay, so all we can do is the changing of the delta S. But when you can focus on the randomness by using statistical thermodynamics, then we can have closer or deeper insight of S. Okay, I will introduce that later. And we can notice that, yeah, we can see this. If T2 greater than T1, which means that T increase, of course, S increase. S increase. And if the volume increase, the total S will increase. Okay, of course, this is kind of obvious, right? If you heat up something and the randomness of the molecule will become greater and greater, so you'll increase entropy. And if you make the volume greater and greater, the randomness of the volume, randomness of the molecule has more space, so they can be more random. Okay, so increase the entropy. So this kind of makes sense. And also you can see that, yes, it obeyed this equation. 好，我快速的讲，就是如果今天把前面的事情再加上更多的条件，就是理想气体，我们就会多加这2个。然后我们就把刚刚前面的第一个式子再把它带入进去，就会发现得到这个式子。这是看起来很直观。你看哦，升温的话，你就会增加你的 entropy change。如果你升体积的话，你也会增加你的 entropy change。就这样，好，谢谢。I will see you after 20 minutes. If you have any questions, come here. Thank you. 好，我们感谢大家回来。跟大家聊个小事情，就是这几天发生的哈。我有一个好朋友，他是一间公司的 CEO，OK，大老板。然后他现在正在上 EMBA 的课程，然后 EMBA 就是，然后那个 EMBA 课程就是很多也像他一样是老板 CEO 的那种，然后去上，然后那些 EMBA 其实就是要教他们如何有系统性的经营一间公司就对了。那是啦，先 screening 嘛哈，然后呢，助教就传讯息，就是说，哎，你这样不行啊，你要重你要重新那个重写这样。结果为什么总是找不到？然后结果反正我就知道这件事情，然后他当然有去解释他。那解释完以后， 那个教授就说，好，我相信你是自己写的，你只是拿它当做是润饰的，就是文法润饰的，然后就这样。那他就我就跟他聊这件事情，我就说你不怕那位教授就是只是口头跟你说好，我接受，你不用再 submit 第二个版本啊、他只是口头接受，但是之后给你很低分嘛，我就这样跟他讲，然后他就说哦我不管啊，反正我自己写的，我只是拿来我上这门课我不是拿来得高分得高分跟就是跟自己的上司说我要加薪这种，因为他没有上司，他就是上司。然后他就说我只是要来学东西而已。然后我当下我有一点吓到，就是我从小到大都是一个想要拿高分的人，然后我我都没有想到，就是说，哎，其实学习好像是为了要学东西，而不是要拿高分。但我当下的直觉的反应就是，哎，你不怕教授说教授口头答应你，然后给你很低分吗？就是我的思考就是完全就是会拿低分这件事，我会为了要低分，所以我我即使是我自己写，我只是拿 AI 来 polish，就是来弄那个文法，但是都是我的 idea，这是我写的，那我有检查过，我有修饰过，那他就说没关系啊，这个我只要我学到东西就好了，然后我就觉得哇，这个就是我这种小鼻子小眼睛跟老板的差别。为了要高分，然后这种不知道大家觉得怎么样？当然了，我在获得高分的时候，我也有学东西啦，但是我只是觉得这个心态好像不一样，就是他纯粹是为了学东西，低分没差，然后别人对他的评价也没差，因为他已经是 top。那我我的话，我就觉得说啊，我从小到大，应该说我也是从正常家庭这样子学习这样啊，然后对啊，就一直都有上司这种感觉，所以我就想说，哦，这个就是差别所在啊，让我觉得有点汗颜啊，就是人家是为了学习而学习，我是为了高分而学习，我是为了获得某些目的而学习。当然，这也不能怪我，因为我我就是没有资源嘛，对不对？哈，我就必须要努力去让别人认可，然后得到就是前往下一阶段的路，这样，所以还蛮有趣的一件，就是这几天发生的事情，让我有点思考，就是我到底是为了什么？对啊，蛮有趣的。那当然啦，各位在这边也是都是要学习嘛，然后有哦，对了，这也就是为什么像刚刚我提到那个许家伟同学，他其实功课不好，你知道吗？他的功课并没有就是哇考试考很好，没有哦。但是在专题生的时候，他就是学得很无聊，他就觉得啊好没劲，然后考试也不会考很好，就只有过而已这样。那他就来到我的实验室，但是我问他问题，他的材料的，例如说热力学或者是物理冶金，他虽然没有考很高，但他的观念都是懂的欸，而且他懂的都比其他考的好的人还要多哎。这时候我就觉得，哇，这人只是不会考，就是他只是不想考试而已嘛。他如果真的想要考试的话，其实会考得非常非常高，因为他观念是非常非常正确的。所以它也是一种为了学习而学习，而不是为了高分而学习。然后也难怪他现在就可以也难怪那时候他就会自己去想要去学AI 哦，他觉得自己有兴趣，他就是想学。然后没有人会哦，当时的材料系是没有人会的，那顶多就是我会写程式嘛，那我就跟他一起讨论。所以当然我也帮他找了一些我认识的专家来一起指导他。 那所以我就觉得，可能真的学习是那样子的心态的话，对长远来看，好像真的是好的，这样。嗯，不过我都已经44岁了才了解这个道理。可是也不是，我不敢说我了解，我只是说我发现我自己是一个为了考高分、为了别人认可而学习的人。那不知道你也是不是这样？哎，那我就觉得好像是不是要改变一下？Anyway，这是我的最近的思考。然后人老了就会比较想要，就会想一些有的没的。那不然的话就太无聊了哈。好，来 next。Next, I'm going to introduce TDS equations. TDS equation. You can see that after combining the first law and second law, you obtain this one. TDS equal to blah, 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 blah. But it is difficult to use this because this du and dv and p, they may do material properties, different material properties. Material properties good to use because you can measure and apply it and calculate that, right? But du p dv is kind of, too deep. It's a kind of something deep down. We want to use that. We want to use something that's easily to be determined, easily to measured. Okay, so that's how we obtain TDS equation. We apply some mathematics to decipher into the three forms. Everything, the three forms here are all equal to TDS, 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 but they are related to different properties. All right, so I would say the reason why we learn TDS equation is it is useful. Useful. Okay? Although all these TDS equations are equivalent to the TDS equal to du plus PdV. All right? So this is just useful. Why? Because we can obtain the bar QR. Okay? Because TDS is the bar QR. Right? The second one, you can determine S by integrating the equations and divide by t. Yes, because when you push this t to the right hand side and then do the integration, and then you can get the s. Very useful. The third advantage is that the equations can use measurable, as I mentioned, measurable properties. It's something can be measured, can be determined easily, like Cp, like beta, like kappa, like temperature. All right. The fourth advantage is to find Cp minus Cv. Well, I will introduce that later, like several pages later, you will know what I mean. And if the S equal to 0, you can determine the relationship between T, between V, between P by using this equation. So there are 5 advantages to learn TDS equations. All right. 好，为什么要学这个 TDS equation 呢？我们当然都知道，我们结合了第二定律以后，我们就得到 TDS 等于 du plus p dv。这个很棒。但是 du 跟 dv 啊 ds 这些都太深层了，我们很难用。那如果今天我们可以使用一些我们本来在实验中可以量测出来的数据，量测出来的性质或算出来的性质，就可以把它替代掉，那不是很好吗？那这里就是我们如何用数学的公式把它们解析出来，把这个深层的意思解码成我们平常看得懂的语言，这种感觉啦，比较容易去计算的东西。那还有什么功能呢？它可以算 debug Q 啊，这就是 debug Q 啊。 它可以算 S， 只要把 T 移过去做积分就可以得到了。而且重点在于，就我刚刚讲的，它使用的是 CV、CP 这些，还有贝塔、T 啊、kappa 这些东西都是 measurable property， 叫做可以量测的性质。接下来我们还可以看到 CP 减 CV 是多少啊？这个下几张投影片就会教。那 ds 等于0的话，把这边等于0，你就会发现哦，其实 T 呀、V 呀、P 呀都会有一些关联性，就可以用这边来找出来。所以有这5大优点，那这个是为什么我们要学接下来的 TDS， 就是为什么要去推导它了啊。Okay, so let's continue our proof for the TDS equation 1. Oh, by the way, why there are three forms of that? Because we can't just changing the variables. The function S is a function of something, right? A lot of change. Change something can change entropy. Okay, so based on different condition, you can regard the S entropy as a function of TB, TP, or VP. So all we need to do is just changing the variables. All right, so that's first one. We try to change temperature and volume to make the S as a function of temperature and volume. Okay, so temperature and volume. So how can we make? Okay, the problem is now du. Can we transform the du into the function of temperature and volume as well? Yes, we could. So that's how we do that. We make the du as a function of temperature and volume. Temperature and volume. Okay, of course, this one, they are slope. Okay, then we use mathematical tool and some knowledge. Partial u over partial t at partial u over partial u over partial v at constant t is this one. Well, please go back to your textbook section 6.7. They have complete and straightforward proof for this. So I won't mention this here because of time limitation. We also know that the u here, partial u over partial t at constant v, is actually CV. All right. So these two things, well, you can either learn from the previous few page or in the textbook. All right. So after your substitution, T partial P divided by partial T, V dV equals, minus A dV plus CV dt plus P dV. Okay, so cancel. All right. And good thing is, well, difficult things, partial P over partial T is difficult for us. And partial P over partial T at constant V is difficult for us. So how can we make it easier, which is very similar to, decipher it into something we are familiar with or measurable parameters. We found that we can apply cyclic rule. Remember cyclic rule, right? Something times something equal to -1, right? We introduced the mathematical tool last PDF, right? Okay. List PDF. All right. So minus. Remember that. Partial V over partial T at constant P. So this trick can kind of make something at the constant limitation become partial V, and to different partial and constant P, constant T. Wow. And then you find that, hey, this is beta, this is kappa, the expansivity and compressibility, I guess. Anyway, you remember this beta and kappa. You remember in the review 1, right? So they are actually the measurable properties. So if you substitute this here, and you can see, okay, TdS equal to CV dt, T beta K over K, beta over K, and dV. Okay, so that's how we obtain the first TdS equation. 好，那我们就讲 TdS equation 1怎么来的。那刚刚讲到 entropy 其实就是可以有很多个改变它的方式。那所以这些 TdS equation 纯粹就是改变不同的parameters 不同的参数来去看它的变动，看 entropy 的变动。好，那第一个是 Tv 的变动。好，那 Tv 的变动 TdS 乘上 du plus P dV 嘛，这是一切的根源。那 dV 已经 OK 了，这时候就把 du 要改成 T 跟 V 的函式写出来就好啦。写出来完以后，这些叫什么？斜率，这些斜率呢，这个斜率是可以在会等于这个东西，它是在课本里面就有了，那这还蛮直观的哈，那我就不讲，那你回去看一下。然后这边的话 ，partial u partial t，constant v 的话是 cv， 这前面也都教过了，所以我们把它带入进去以后，带到这边来就发现 p dv p dv 可以消掉。那但是这边有一个很丑的东西，没看过，那怎么办呢？这时候有一个巧妙的数学公式数学的工具叫做 cyclic rule， 还记得我们曾经教过这个数学工具，它是可以把3个 x、y、z 的变数的个别的 partial 乘在一起会等于-1嘛，还记得吗？哈，那这时候就可以使用到它咯。结果我们就可以发现，这样子可以把 v 在 constant v 的状态下，我们把它可以转换成 partial， 以 partial v 为主。对另外2个做微分啊，那结果发现运气很好，就是那 VTP 跟 VTP 跟 VPT 好这种东西，它就是我们之前介绍过的expansivity 还有什么 compressibility 之类的哈，那这两个都是材料参数啊，材料参数。好，那我们就可以把这个顺利的取代掉，就变成第一个式子了。那这第一个式子就可以用可以量测的参数跟这也是可以量测 ，CV 也可以量测哈。然后还有我们可以量测温度变化、体积变化，就可以得到 TdS 咯。哦，非常的精准。OK，a TdS equation 2 just changing another parameters. All right, parameter S is a function of temperature and pressure. Let's change V, replace V as a P. All right, then let's continue. TdS du. And what is PdV dV things? All right, and we focus T dot P. Who is a function of T comma P? H, right? H is something focused on temperature and pressure. And you can see this is for phase change. Right, so you focus on H. You know that you need a help from H. So H equal to U plus PV, no problem, and du equal to dH minus PdV minus PdP, no problem. So we substitute du to here. So dH minus VdP. Okay, because you can, they are cancelled. PdV minus PdV. All right, so something left here. And again, your h is function. We do exactly the same thing, just like what we do in the previous page. Partial h over partial t, constant p dt plus partial h partial p t dp minus v dp. Okay, these two terms is exactly the change of h, and the contribution will be dt and dp, two contributions. Okay, exactly what we do for du in the previous page, right? And then we will, change to the right hand side, to the right hand side, to the right hand side. This one somehow ugly, okay? But the S now is also we want to see the S change due to the temperature and pressure contribution. So this is actually equal to partial S over partial T at constant P, right? This is a slope, right? And this partial S over partial T as constant T. So you see, this change can be contributed by change of temperature, change of pressure. Of course, their coefficient should be the slope, right? This is slope. Yes. So if you know this is a slope, you know that Maxwell relationship, another mathematical tool I introduced for you previously, is if we make it partial T here, and right hand side, if we make it partial T here, they should be partial as double differentiation, double partial, W, partial P, partial T, and the right hand side is partial S2, partial T, partial P. They need to be the same, right? This is a Maxwell relationship. And the point is, what is that? So all we need to do is do this one, do the partial P. Okay, this one for partial P, this one for partial T. And then I would like to write down here. All right. So we can obtain more information based on the Maxwell relationship. So equal 1 over T partial 2H over partial P partial T. And the right hand side is more relatively ugly. Partial H over partial T, T minus V plus 1 over T, partial 2H, partial T, partial P, minus partial V over P, T. Okay, oh, perfect. Right, ugly, but luckily we can, cancel each other. And then you notice that the blue part, okay. Well, okay, this blue part equal to the rest of it. Okay, the rest of it become this. So ugly, right? 好，我们开始讲，还没完呢，not finished yet. I will continue in next page, but I can go give you a translation now. Okay. So let's take a look. 中文，对不起。第二个方程式哈，我们就转换，刚刚是 Tv 的函数嘛哈，温度跟体积的函数，现在变成温度跟压力的函数。好，温度跟压力，那我们想到什么啊？就想到 H 嘛，H 也是通常我们也会把它看成是温度跟压力的函数。为什么呢 ？H 是在做 phase change 嘛，哈，就是叫什么相变化哈，相变化那个平台还记得吗？哈，好，那我们就使用 H 把它写出来，它的叫什么？它的变化量可以，那变化量写出来以后呢，我们就把 du 带到这公式里面去。那这公式写完以后呢，就得到这样子的式子，那很高兴的把它删掉啦，就变成这样而已。那刚刚怎么做的啊？刚刚我们是说，我们把前一页我们是把 du 变成两个贡献嘛，对不对哈？那现在我们把 dh 也变成 t 跟 p 的贡献，就写成这样子啦。那这样子写完以后呢，我们就可以把它就是整理一下，然后把 t 移过去，就可以得到这个丑丑的式子。那 ds 就会是底 t 跟底 p 的底 s 就是 s 的改变量就会是因为底 t 跟底 p 两个贡献得到的。OK， 好，但是这时候我们又知道，我们现在就是要看 s 是 t 跟 p 的函数嘛，所以说这个式子的这个系数就是我们的斜率，对不对哈？好，也就是说这边是我的斜率长这样，这边是我的斜率长这样。好，那这时候我们借由我们之前介绍给大家的马克斯韦尔的关系式的数学工具来看，我们只要把这边对 P 做微分，这边对 T 做偏微分，好，偏微分了哈，偏微分，两个都是偏微分，我们其实会得到相同的式子，这两个是相同的式子，也就是说这两个再做个微分，它们会相等，那这样我们就会多了一个讯息资讯是我们之前不知道的。好，那这时候我们就赶快把这边对 P 做微分，这边对 T 做微分。理论上来讲，这两个结果是要相等的。好，结果就发现这个蓝色的部分会等于这个丑丑的东西。那我们会用这个丑丑的东西再继续做下去哈。So we will use this blue part and it's the expression, and we will use that later. Okay? Right. Right, let's continue. So again, this is the blue part. The blue part equal to this. We obtain here, right? Okay, and again, this one is CP, okay? CP. So luckily, TDS equal to CP dt minus T partial V over partial T P dt. And luckily, you see, partial V over partial T at constant P is expansivity, right? So this one divided by V is expansivity. So this can be write down V beta. All right, so this is the second equation. 好，我们刚刚讲到用蓝色的这个东西，就是得到这个嘛，哈。上一页千辛万苦用 Maxwell 关系式就可以得到这个式子。那这个又是 CP， 这没有问题吧？哈，我们已经写过很多次啦，结果就得到这个式子啦。那这时候还差这个，这个就是体积的对于温度的变化在 P 为定压状况下，那这个不就是 expansivity 吗 ？beta， 这是可以量测出来的哦，这是可以量测出来的。所以呢，我们只要把 V 移过去，我们就可以把这个东西取代啦，得到第二个 TDS equation。好 ，next third one, I won't guide you to prove that. Please go back home and try your best. And this is another problem in the textbook. All right, so you can do that. It's easy. Okay, don't worry. And then remember that TDS equation has the fourth advantage, which is you can determine what's the number, CP minus CV value. So how can we do that? We have equation 1, we have equation 2, and both of them have the left-hand side TDS. So actually, TDS should be equal, right? So dt equal to, wait a minute. Okay. dt equal to T beta dV divided by kappa Cp minus Cv plus dV beta Cp minus Cv dP. Okay, by connect them as an equal sign, by the equal sign, you will have this one. And you see the T, the change of temperature is actually have two contribution, dV and dP. So T is actually temperature, and temperature is the volume, and T is a function of volume and pressure. Okay, so you can see that here, dV, P, P. All right, so based on this, you know that dt equal to partial T over partial V P. So you can see this is a slope, right? Slope again. So now let's highlight this. Partial T over partial V as constant P is actually equal to this one, right? So now you can determine Cp over Cp minus Cv equal to T beta over K times partial V over partial T, okay? Because they inverse. And luckily, this one, again, V beta. Previously, you see that, right? So Cp minus Cv equal to T beta divided by kappa times V beta. Okay, so this is useful to calculate Cv of a solid because Cp is easily measured and Cv is relatively difficult. Okay, because it's really difficult to control volume, right? You easily control pressure, that's okay, but it's difficult to control volume to change the heat, right? So you can use this relationship by obtain Cp experimentally and determine Cv theoretically. Okay, this is the best thing that Cp minus Cv works. And Cp minus Cv is always greater than 0. Okay, this is kind of experience. And please prove Cp minus Cv equal to R. For ideal gas. Well, you can prove that back to your home by applying PV equal to MRT. All right, so you can do that. 好，我们现在讲 CP 减 CV 这个叫什么？好处啊，我们不在第4个好处就是这个东西嘛。那我们说，就是第1个式子跟第2个式子左边都是 TDS， 表示说它们是相等，所以我们就画个等号吧。我们画完等号以后，我们就发现，哦，这个底 T 会等于这个横轴的式子，但是不用担心，你看哦，底 T 跟底 V 跟底 P， 好，表示说温度是 V 跟 P 的函式。那 V 跟 P 的函式的话，我们可以把这个写成这样。 那前面这两个当然就是斜率啊，这个斜率。那这个斜率是，我们就把这边黄色的跟这个黄色来比较一下，我们就会发现 ，OK， 这个 CP 减 CV 把它弄到就是可能就把它放到左边去，然后这个再把它除过去，那这边就变成 CP 减 CV T 贝塔卡帕，然后这边已经转过去了嘛，所以它要倒过来。倒过来以后发现，哦，原来是长这样。那这个运气很好，这个东西又是 expansivity 乘上 v， 所以这样子你就可以得到 Cp 减 Cv 就会是 T 贝塔除以 kappa 再乘上 v 贝塔。OK， 那这有什么好处呢？这就是因为我们在去计算，就是量测 C 的时候，比较简单的量法就是定压去量它的 capacity，heat capacity。但如果今天是要量 CB 就比较难，因为你很难去真正的控制一个东西的不要缩放嘛，那实在太难了。你要固定它每个点这是不太可能吧所以说我们通常都会是定压的状态下去量 CP。那怎么样拿到 CV 呢？就用这个公式去反算出来就好了这是它厉害的地方。那 CP 减 CV always greater than zero， 然后 CP 减 CV 是for ideal gas 要怎么做呢？你就带个回去算看，我记得它也是作业的一部分，我是说 textbook 的作业一部分。然后就很简单带个公式就可以算 PV 等于 RT 就可以算出来啦。Okay, so we just finished two TDS equation. The third one is easy. Okay, you can think how to prove the third one by using the first one and second one. OK， 你可以用第一个和第二个算算看，怎么样推到第三个。好，这很简单，你自己想想看。好，回家试试看。All right, so example, easy example. If you have a copper at 1000 K, atmospheric pressure, well, it's normal, right? And beta equal to blah, 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 kappa, CP, and what is CV? Okay, again, we know that CP minus CV is this one. So, I mean, this example is very realistic, very practical, because you know how to measure the beta, measure the kappa, and measure the CP. Difficult to measure CV. Okay, so that's really a practical problem. V equal to capital V divided by N. Okay, and V is M. I mean M divided by low. Okay, this of course M divided by low is the lowest density. Density. N can be rewritten in the next one. It is 63 point 6 kg K more minus 1 and divided by 8.96 times 10 to 3 kg m minus 3. Okay, of course, this value, this value is actually obtained by this kappa. You need to Google it. Okay, you can get the density and you can measure when the kilomole, how much kilomole for your mass and what is density, and you can obtain its mass. All right, so you even I didn't provide here, you can Google it and you can obtain the material properties. All right, of course this is not exam. if we give you an exam problem, I will provide all the detail because you cannot use Google, right? So anyway, 7.1 times 10 to the minus 3 and 3 K more minus 1. So as you can see that this problem still needs you Google that, okay? So you have V here, so CV equals CP minus TV beta 2 copy. So 2T times 10 to 3 joule K more minus 1 K minus 1. Okay, so this is the final result. And let's take a look. This is actually 3 times 8.314 times 10 to the 3. Oh, CV for high temperature, 1000 K, right? Temperature is close to 3R. Oh, okay. This will be some sort of important in the PDF 9. All right. This is PDF 2, right? But PDF 9, we will see this 3R study this, have more deep discussion for this. All right, so 3R CV. All right, for the solid or copper or something. Okay. Yeah, that's it. 好，我们来应用一下刚刚的 CP 减 CV， 它会等于是这个东西哈，我们刚刚算出来的。然后呢，我们题目就是有一个铜，然后在高温的状况下，一般的压力下，然后它的 beta、kappa、CP 都告诉你了。但是问题是我们要算出 V 才能带公式嘛，哈，所以我们要算出它的 V 是大写 V 除以 N。那这时候要怎么样去算呢？我们必须要去这边可能要 Google 一下哈，因为这边有需要用到它的，叫什么？就要假设它是虽然这边没有讲到它是几摩，但是我们还是可以假设就是1K 摩。那1K 摩会有多大的质量呢？必须要或者多大的体积呢？我们就去查一下嘛哈，查它的重量跟它的叫什么密度，我们就可以反推回它的 V。好，所以这边的 M 除以 N 就是它1K 摩会多重哦，1K 摩会多重，然后它的叫什么密度是多少，这些都是要 Google 来的。好，那当然我们如果在考试的时候，我不可能会叫你去 Google 啊，所以一定会给，不用担心。好，算出它的 V 以后呢，就可以带公式得到这个式子。那这个题目重点不在这里哈，那带公式很简单，但是呢，我们要讲的原因是因为，我们发现26乘10的三次方其实有一点接近一个数字哦，叫做3乘上8.314乘10的三次方，是3倍的 I。那这个东西我们在第9个 PDF， 也就是最后一个 PDF 的时候会讲到3R 这件事情。那所以这边有点像是说前后呼应，以后你会看到这个3R 这个数字。All right, next. Next, we kind of change to other topic. We are going to use use the S to help us to study or discuss something that we are, difficult to solve that. Okay. One thing is free expansion of an ideal gas. So there's a condition. There's a story that there's a container, and the container has thermal insulator. Okay, so no heat flow. Okay, and this is a diaphragm, or you can say it's a wall. Okay, previously this is the right hand side is a vacuum, and the other side is V naught T naught. Okay, but if you take out of that diaphragm, the wall has been take out, and then the particle of the gas will freely expand to the right hand side. Okay, so it will reach and T1. Of course, you can imagine that there's no heat change, right? Exchange. So the T0 and T1 is almost the same, almost the same. All right, and we are going to see the equilibrium states T0 R T0 V0, no problem. And this is the initial state, and the final state will be T1 RT1 D1, no problem. Okay, and B1 initially 0, of course, 0. Okay, and the process is irreversible. Oh, this is really important. It is really difficult for us to make all the atoms go back to the left-hand side without adding work, right? This is difficult. I mean, impossible. So this is irreversible because after you freely expand, you cannot control all the atoms go back to the same region without adding work. So this is irreversible. Okay, right. But because this is irreversible, okay, and then we want to determine the delta S change. We want to see the randomness change in these two cases. How can we do that? Can we determine that? Yes, we can. We can estimate that after 10 minutes. All right, so see you later. If you have any questions, just come here. Thank you. 喂，哇，第三节课大家辛苦了，我也很辛苦了啊，加油！嗯，要聊些什么呢？嗯，跟大家聊一些很玄的东西好了。这是发生在3年前吧，就是好，我儿子呢在好，反正应该这样讲，2022年的时候，我在美国 sabbatical 啊，我就休息了大概8个月啊，8个月在美国，我们全家都去了这样。然后呢，回来到台湾以后，呃，我的小朋友就是就去光复高中的附设幼稚园，1个月要2万块，好，然后就幼稚园嘛去，然后上了2个月之后，忽然我们发现，哎，我们抽到了一个东西，抽到一个叫做赌型非营抽到的，1个月只要2000块。OK，好，光复高中的那个附设幼儿园在我家旁边，开车3分钟，2万块1个月。那非营利幼儿园1个月2000块，在哪里呢？在笃行路，这很远哦，你知道在哪里？你知道吗？几乎就在台积电啊，然后旺宏啊，你知道在哪吗？就在甚至在介寿路那个介寿路跟金山路那个在更里面，就是深入园区就对了。所以我每次开车大概反正都要1个小时就对了。OK，就是去那边1个小时，然后再回来到交大这样。当时就有2个抉择，就是要不要转过去啊？当然现在已经转了哈，等下告诉你为什么。所以我现在每天都是1个小时前就要出发，然后载他到笃行幼儿园、非营幼儿园，然后再交大，所以大概要1个小时。但是如果以前的话，就是只要去3分钟就到光复那个。好，你要怎么选？那当初我就在想，因为接送是我嘛，对不对哈？那我就觉得说，哇，我每天都要多花1个小时接送，好累这样。但是就要花比较多钱，2万块，那一个是2000块，差10倍的价钱。那送那么远就可以省一些钱，我送这样。那所以我太太当然就说，就换啊，就换到笃行幼儿园就可以2000块哦。我心想说，对啊，那是因为是我送啊，对你来讲没差，但是家里的钱就可以少一点。所以我那时候就想说，到底怎么办？当你跟你的太太有无法叫什么，无法达到共识的时候，该怎么办？我们就去拔杯，我们就去我们就去行天宫拜拜。因为这个时候你知道，已经是我们2个都对嘛，2个都有自己的理由，但是无法才得到共识，那该怎么办？但是可能也有人就，刚刚我那时候就觉得说，哎，是我送，所以我应该可以决定吧，这样，然后钱也是我付，我应该也可以我决定吧，但没有，不是这么一回事，夫妻之间不是这么一回事，所以2个人无法得到共识，2个都对的时候怎么办呢？我就去保杯，那我们就行天宫保杯。然后那时候我去行天宫，我就问说这个关圣帝君啊，什么就是就就是请问该不该换？该不该换？然后你知道宝贝其实它是可以，就是一正一负嘛，就是表示说是这样那好像有一个叫什么叫什么笑杯跟不行，是不是还之类的？笑杯的意思就是说你好像刚刚讲不清楚，或者是说神明觉得这件事情很好笑，不想回答之类的。OK，那这时候我就宝贝哦，我说请问我要不要换我儿子要不要换幼儿园呢？不，笑不会 OK，然后就 OK，好，是我讲不清楚吗？我再仔细讲一次。
小杯，第二次又是小杯。我想，奇怪，我讲的很不清楚吗？我就再仔细的讲啊，给他很多 detail，给神明很多 detail，还是小杯，3次咯，3次咯。然后我想说，怎么会这样？是1/4的3次方嘛，对不对？哈，很低，对不对？接下来我就想说，是不是我问的不对？我就说，好，请问要不要转？可不可以交由我周文帝决定？我就问，又是校规。然后这时候我就觉得超怪的，为什么已经4次了，4次校规哦，超级低几率哦。然后我就想说，到底怎么一回事？这时候我太太就说，那换成让小孩本人决定，就是适合让太太决定。就他没有，他就说小孩决定。结果我就说好，那是否可以让小孩决定？然后我就就是一正一反哎。然后我就回到家去问我的小孩子说：“请问你要换吗？”我说要换。他说因为他想要新，那他就我不知道他那时候为什么喜欢换了，但他就说要换。我说我那时候才3岁而已哦，他也不知道什么比较好，什么比较不好，然后他就说要换，好，我就听从他的指示就换了这样。不过我觉得这个故事也蛮有趣的，就是对啊，小朋友要不要换幼儿园，就尊重小孩子的意见嘛，小孩说要换就换嘛。所以前面几次就是问神明说要不要换，那他说不是我的问题啊，然后接下来第4次是我能不能决定，爸爸能不能决定，也不是你可以决定的啊，他也在笑，所以我就觉得蛮有趣的，就是1/4的4次方的几率。然后让小朋友决定这样，我觉得蛮有趣的，那就跟大家分享，这个几率非常非常低哦，1/4的4次方啊，还蛮酷的这样所以冥冥之中好像还真的有些什么，对，虽然学科学嘛，但是终究还是我觉得这个力量，也是还蛮玄的。好，那我每一年都会讲这个故事跟大家分享这样，然后但是到最后都会遇到一个麻烦，就是不知道该怎么用英文翻译，不会要怎么翻译，不会。然后有一次我就跟大家就是跟其他英文老师分享这件事情，然后英文老师说，哦，宝贝就是一个英文，但我还记不起来啊，那你自己想想看这样。Anyway，so this story tells us we need to respect kids' opinions, right? Let them decide. Let them make their choice. All right. Okay, that's it. 好，next, we just talked about the free expansion of an ideal gas, right? So it's difficult to make every point go back to its original configuration. Okay, it is impossible to make all the atoms go back to its original shape. So this is irreversible, clearly. But it's really difficult for us to determine the delta S. We want to see the change from this to here. What's the delta S? We don't know. Okay, it's really difficult. So because we know that the T0 and T1 is kind of almost the same because they are in the thermal insulator and it's the ideal gas. So how about we use alternative way to determine the delta S? If we can find and wait a minute. Well, 好，不好意思啊，我的小抄没电，我必须要用我的手机了。等我一下，小抄对我来讲非常非常重要。我已经跟你讲过，就是我我其实跟你上课的时候，我的脑袋其实是放空的，我只是专注于把我的嘴巴讲的话讲清楚而已。好，等我一下哦。View two Okay. Right. So, can we assume a reversible isothermal process? We can determine the delta S in this case. But if we can determine this delta S and the reversible isothermal process has the final and initial condition the same as this, we can determine delta S because S is a state function independent independent about the path. So this is one path. This is another path. But if we have similar initial and final condition, we can determine the delta S. Okay, that's the idea. So we know that the du equal to 0, dbar qr equal to 0. And we know that the dbar w also equal to the 0. But we want to know the delta S. The delta S irreversible. We want to know this. This is irreversible. I highlight by yellow. Okay. Can we determine this? Can we just determine the delta S? It is reversible and also isothermal. Because in this case, we know how to determine delta S. We know how to determine this, but we don't know how to determine that. But as long as the initial condition and final condition are the same, they can be equal. Okay, so now we focus on this. So assume a reversible isothermal process in order to calculate delta S. The entropy change in this case is ds cv dt t p over t dv. Okay, so the system, this system, we also can call that, yes, this is reversible and isothermal. Okay, we know reversible isothermal is the delta S is R natural log V1 over V naught. Okay, so actually, yes, this we can say this is delta S irreversible because they has the same initial and the same final condition. So their change is equal to the reversible isothermal value. And in this reversible isothermal process, you can say that has work. Their equilibrium work in this assumed process, equivalent work done by the system is actually the work reversible equal to QR. So your R natural log of V1 V over V0 delta S times the temperature T naught, you can know that actually the work reversible work is actually equal to RT naught natural log V1 over V naught. And you see that previously in the free expansion, no work. But in a reversible isothermal process, yeah, you have some work. And this work is equal to the delta S. Well, divided by T naught, you can get the delta S. And the delta S is the entropy change between two states. And these two states also equal to the free expansion of an ideal gas. All right, so this kind of using a alternative way to determine something that we cannot calculate. OK， 好，我们要开始讲中文了哈，就是如果今天在一个容器里面，它是温度的，就是好好的完全完美的隔绝，中间的这个东西被拿走以后，它会从 V0 T0 扩散到变成 V1 T1。当然啦，在这个 thermal insulator 里面啊，哈，它的 temperature 应该是不会改变多少啊，所以这边 T0 T1 我们可以就是稍微说啊，它们差不多啊。好，那但是呢，这个东西很麻烦的事情是，这边有很多 particle， 对不对哈 ？gas 的 particle， 然后我们被expand 以后，它会分布在这里。哎，可是我们不可能有任何一个动作是可以把所有的那些 particle 回归到它自己原本的位置嘛？那不可能，所以这是 irreversible， 就是不可回逆的、不可逆的。但是这种不可逆的，我们就不能算它的 delta S， 但是我们可以假借别的方式去估算它的 delta S 大概会是多少。只要我们使用一个可逆且等温的状态，是我们可以算的哦，我们可以算的这个方法，但是它的初始条件跟结束条件跟前面这个一样的话，我们就可以，反正 S 是 stay variable， 跟路径没有关系。你走了一个不能回复的路径，那我只要走一个可以回复的路径，我们就可以算啦，对不对哈？反正它的就是初始跟结束的状态是一样的，那它们的之间的 delta S 就会是一样的 ，OK？ 因为 S 是不跟路径有关的。好，所以我们就假设了这个东西，这个 delta S irreversible 会跟我们的 delta S reversible 跟 isothermal 这个状态是相等的。那只要接下来我们只要算delta S 是可逆跟等温的状态下的话，就可以算出来了。好，我们就算出来了，那就是用前面的式子嘛，哈，哪一个呢？哪一个？让我想想看 ，natural log 啊，这个啦，这个，对啊，这个 ，OK， 好，就是这个 r natural log v1 v2，然后 temperature 一样嘛，哈，就不见了，对不对？所以就是这个式子 ，OK， 好，那我们就算出来啦。那也就是说，用这种不同的路径，然后去算另外一个路径，它就等效的 delta S。好，我们就可以得到这个式子了。那实际上，这个 reversible isothermal process 其实是有做一点功，让它去改变成 delta S 会有这么多的。所以说，在这一个过程中，其实是有 work 的哦。但是在这个 free expansion 是没有 work 的。OK， 那这边的互相的转换，其实就是delta S 其实就是因为我们 reversible 做的功得到的，那这个 free expansion 其实可以等效于，就是说它的 reversible 的 work 是这样子的值。好，总之，这边的重点就在于说，原本不能算的东西，虽然它有但是它有初始值跟结束值，那只要使用 delta， 就是 S 用可以算的话，它是路径是独立的，是没有关系的。好，所以你就可以用这样的去推估其他的不能算的 delta S。OK， 好 ，continue， almost there， chapter 3。So now let's take a look entropy change for liquid and solid. Previously, we talked about entropy change for gas, ideal gas. What's the difference between gas and liquid or solid? Liquid or solid has a significant difference between with gas is that the volume change is relatively small compared to gas. You can imagine that when you heat up the gas, it will expand dramatically. But for the liquid, for the solid, if you heat it, it will change relatively small. Okay, so that's what we're going to see here. So now volume change. V is a temperature and pressure functions. So you can change the volume can be treated as two contribution, dt and dp, and their own slope. Okay, so let's take a look. What will it looks like? So dv equal to beta v dt minus kappa v dp. Actually, we've done that before, right? All we need to do when we see the volume change, we do the differentiation. Okay? So the V, there's a V here. So volume should change during the process, right? Suppose we doing a gas. Yes, the change of V need to be considered. However, because now we are focused on liquid and solid has relatively small volume change compared to gas. So we can assume a small change, V approximately equal to V naught. So the dV can be, this V can take out to the outside. And also V equal to approximately equal to the original shape, original volume. So your dV can be treated like this. And the value is V, the result, V naught 1 plus beta T minus T naught minus kappa P minus P naught. Okay, so if you take into account of the small change, V approximately equal to V naught, and your V is actually final V's here. Okay, and because you have the volume change, you can use that to determine further for the entropy change. So as soon as small change like this, yeah, and you substitute the TdS equation 2, okay? You see the entropy. Entropy is temperature and pressure, and you substitute TdS equation 2, and you find that your TdS equation Cp dt minus T V naught beta dP. Okay, you substitute that, and your ds can be rewritten like down, and you do the integration to get the actual S change. So S minus S naught equal to Cp natural log T over T naught minus mu naught beta P minus P naught. Okay, so that will be useful for determining the entropy change for liquid or solid. All right. So, well, the most important concept in this page is that because liquid and solid has relatively small volume change. Okay, so when you introduce this introduce this condition, you can rewrite the entropy change. 好，这一页要讲的东西就是熵的变化。之前都说熵的变化跟是 for ideal gas，OK， 是 for 理想气体。但如果今天是 liquid 或 solid， 流体或是固体呢，会有什么样的现象呢？好，那首先要讲这个东西的时候，之前要先讲要讲熵的变化之前，要先讲体积的变化。那体积变化率是其实在 liquid or solid 其实是非常非常小的，相对来说，对理想气体来说。好，那我们就来看看理想就是体积变化是怎么样呢？所以 dV， 然后要算出来应该说 V 要对于温度跟压力的变化，它的贡献可以写成这样子 ：dT dV dT dP 的贡献还有它的叫什么斜率。那接下来呢，我们就把这个东西跟这个东西把它改成我们之前都学过了贝塔 V 跟kappa V 负的 kappa v 嘛哈。那写出来以后，我们要看它的 volume change 对不对哈？我们要看它体积变化，我们就做积分就好了。那个 v 呀、有个重点哈，就是说它其实在 liquid 在流体跟体积固体里面，它的变化量非常非常小，所以呢，我们可以假设它就是维持常数。那维持常数有什么好处？它可以拿出去在积分符号的外面 ，OK？ 那所以呢，它的差别很少，也就是 v 跟 v no 是相等的，我们就可以把 v no 拿出去外面啦。然后呢，经过这个积分以后，我们就可以得到 v 其实是 v no 一加这个东西。好，那有了这个式子以后，我们就可以利用它继续去算 entropy change。那 entropy change 的话，一样，我们这边是 TP 嘛，我们就用 TP。那使用的是 equation 2，TdS 的方程式第二个。那一样还是要假设它的 v 约等于 v no， 也就是它基本上是没有什么体积变化的。然后呢，我们使用它以后呢，我们就可以就代入那个 v 就代入 v no 嘛，哈。然后呢，我们要做就是积分，好，除以 t 以后做积分，我们的 entropy change 就会写成这样子。OK， 也就是说，以前对 ideal gas 或者理想气体的话，你可能做积分会变得比较复杂，因为你的 V 会随着你的变化、温度和压力的变化而改变。但是这边的话，你就可以省略这个变化，你就可以写的比较精简一点啊，大概是这个样子。然后以后应该也会使用到这个。All right, okay, let's we finish review 2, so we are going to review. After the review 3, suppose review 3 should be in midterm 1 range. Okay, midterm 1 range should be review 1, review 2, review 3. But as we mentioned before, that there will be a lot of events, university event or department event hold for the next half of the semester. So yes, we need to give you midterm 1 and 2 and final in the we'll concentrate in the next half of semester。还是一句老话，就对不起哈，就是虽然1到3 review 1到3是第一次期中考的范围，但是因为下半学期有太多的学校或者是系上的课，就是有一些活动我不能上课这样，那所以我们就把考试都比较集中排在下半的学期，那这是很不好意思的事情，因为又改成16周嘛，所以说进度都会比较赶一点，所以不能有任何的，例如说台风假，其实我就蛮担心今天放台风假，好，那对小心一点，这样才可以赶课，好 ，OK。So yeah, review 2 done. Okay, review 3. As we did last time, if we introduce review 3, we need to introduce some useful mathematical techniques tool before we officially enter PDF 3, review 3. So the first one is Lagrange transformation. Lagrange transformation is a really useful tool to change the parameters, change the function variables, right? So for example, if you have a function called z, which is a function of x and y, so of course you can say something like this. Your change of z can be contributed by dx and dy, and the capital X and capital Y are the slope. Okay, but sometimes you want to use X and Y, the slope, as a variables rather than small x, small y. To put it simply speaking, you just want to change the variables, swap the variables. How can we do that? We use Lagrange transformation. Okay, so the trick is that the smart mathematician, they come up that you can have a new function n, which is a function of x, capital X, function of y, okay, which is equal to z minus small x times capital X minus y, small y, capital Y. This is really, it's a new trick. How can the mathematician find out? We don't know. They are genius. Okay? But they found that, okay, n capital X, capital Y can be written in here, dm. dm is dz minus x dx minus y dy minus x dx capital minus y d capital Y. Okay, don't you think this dz minus x, capital X dx minus y dy, yeah, that's it. So they can be, determined. So actually 0. Put the left hand side 0, right? So dm equal to minus x d capital X minus y capital Y. Wow, you successfully make the change of n new function is a function of capital X capital Y. Yes. Although you see that this, what does that mean? It's okay. It's just a tool, all right? You will use that when you actually using this, and then you will find out the purpose of this. Okay, and let's take it more relative to the real world. Actually, the capital X and capital Y and small x, small y, they called reciprocity relationships. What does that mean? Kind of, interact together. It is 相互的关系。They have relationship to each other. And what does that mean? Very straightforward or very simple example is that if you have a plot, if you have you see, you change the V here, but now you don't want to see, I mean, you change the V and you see the change of the pressure, but actually you can see other way. Actually, you can say you see the change from the pressure and how the volume change. Okay, so basically you see the same thing in different approaches. So this is very similar to sort of a reciprocity relationship, just like this. OK， 好，我要讲的是李建德转换。好，这个转换其实就是把一个函式原本是小 x y 跟小 x 跟小 y 的函式，要把它转成它们彼此的斜率的那个斜率的变数，当做是它的新的函式的变数。好，那也就是把它的斜率最后变成新的函式的变数，交换。那当然他就是说，哎，你就直接把原本的 z 啊，你就设定一个新的 m， 然后把原本的 z 减掉相乘，这样就好了。 我说哦，这到底怎么想出来的？我也不知道，他们很强啊。但是做出来以后发现，哎，真的可以把这个黄色的地方取代掉，真的就把 m 写成 x 大写 X 跟大写 Y 的函式，啊，很厉害。那这个小写 x 跟大写 X 之间的关系，有一点像是就是它的英文叫做 reciprocity 的关系，其实就是相互关系。这有点什么意思呢？就有点像是我们在看一个东西啊，我们量测 P 跟 V， 我们改变 V， 它的 P 就改变了嘛，对不对？所以我们可以画出这张图。一开始我们看的就是，我们如果是以这种角度来看，其实我们就哦，改变 V， 它的 P 就会改变。但是实际上我可以反过来看啊，你也可以说，我看这个 P 的改变，我改变 P， 我去看 V 的改变，其实这两件事情是相互关系的，其实就是我们在讲的这件事情。OK， 所以说等一下，当然你看到这个东西啊，这数学这个很奇怪，但是你之后你就会用到它真正在物理的或是热力学的那种实质的性质里面，那你就会知道哦，为什么要这样子。Okay, next, another Legendre transformation. We want to find one of it. One of the xy become small x, big Y. Okay, just change one of it. So the trick is very similar. We say n small x, capital Y. So we just set the n is z minus small y, capital Y. All right. Okay. So dn equal to dz minus y dy minus y d capital Y. Something left is capital X dx minus y dy. All right. So that's another recipe. Just the way previously we changed 2, now we change 1. Okay. Very easy that we only need to minus the one we want to swap. OK， 好，这个很简单，就是延续啦，就是刚刚是换2个嘛，现在换1个。那换1个的话，你只要就是减 y， 你要减掉那个要换的那个就好了，然后也可以得到一样的效果啊，就这样而已。啊，这没什么。Next， well later we are going to use later we are going to do a lot of swapping of the variables. Okay, chapter 8 in textbook just ask us to changing the variables, and turn out changing those variables also give you the physical meaning. Okay, this is the beauty of the thermodynamics. Interesting. 我的意思就是说等一下我们第8章课本的第8章，也就是等一下要做的事情就是不断的去换它的变数，结果还没想到这些换它的变数换成了下一个变数，它其实都是有物理意义所以这也是热力学厉害的地方。好，请接下来继续啦。Next, another thing is that we want to get rid of the undesirable constants. For example, partial v over partial t, the u. Wow, u here is a undesirable variables. This is undesirable constant. How can we fix an internal energy for a system? It's so difficult. How can we do that? How can we get rid of that constant? U is constant, so we want to get rid of it. We want to use V and T, which is more, measurable things for human being, right? So we want to get rid of this constant. So let's take a look. U equal to U is a function temperature and volume. Why? Because we want to use the volume temperature as something that we familiar with. So here we write down du is a change of u, has 2 contributions, dt, dv. slope, no problem. And now, more important, because the u now at this condition is constant, right? Subscript. So the overall du equal to 0, no problem. So while we are going to partial u over partial t v plus partial u over partial v t times partial v over partial t, okay, u equal to 0. So you can see that actually this term is actually from dt, dv, okay, because this is 0, right? So this term is actually from this and this with the equal 0, okay? So yeah, we successfully get this. And then we can further get this one. Don't you think this is really similar to cyclic rule? Very similar, but you also tell us how to get rid of undesirable constants. Next, we also introduce another tools that change variables. Yeah, it's very, it's just pure calculus. You see, UVT. And you can introduce further something, new parameters. But if you times them, they will cancel each other. So you can obtain the previous one. Okay, so this is very just remind you what is a calculus. OK， 好，这一页我们要讲的就是如何去把不想要的常数弄掉。好，这边有一个假设，这个 partial v over partial t 是在量测之下是在 constant u 下。哇，这个 u 是 internal energy， 怎么去 fix 呢？很难吧？哈，在这个实验里面超难的。所以呢，我们就想，那我们可以把它弄掉吗？好，可以的。怎么转换呢？其实就是把 u 把它写成我们要转换成的函式，而且转换完就写出来以后还要等于0，因为它是 constant 嘛，要等于0。那这时候呢，我们就可以把这个 dt dv， 因为它等于0，所以它可以把它结合在一起，变成 partial v over partial t at constant u， 因为它等于0嘛。那这时候我们就可以把这个东西不想要的这个 u 转换成另外其他的可以量测、比较容易量测的，在 constant v 量测，在 constant t 量测，相对来说啦，比较容易的东西。那你不觉得这个式子也蛮像 cyclic rule 吗？好，这边就是一个数学的方法，那之后都会用到。然后还有另外一个 change variables， 我们可以发现就这个东西是我们正常会看到的，但是如果你今天想要把一些你有一些其他的参数，例如说 p 也想考虑进来的话，那其实把它拆分出来，然后它们相乘以后就会把它消掉，就会得到原本的东西。但是搞不好你在计算的时候，你其实是有这些值的，你没有这些值，但是你有这些值，相乘起来就可以消掉了。这个东西其实没有教什么，其实它就是纯什么微积分啊，微积分这个应该你们都学过。好 ，next， 哇 ，implicit dependency。Okay, what is implicit? Implicit 就是 is imply, okay? Imply, so kind of hidden relationship, okay? Hidden relationship. So it's 附带的或含蓄的 something hidden. So we want to using the mathematical tool to find something hidden. Okay. Actually, I'm very tired, so I don't want to continue anymore. So maybe you can just 5 minutes earlier to let you have break and myself too. All right, so I will see you next week. All right, see you next week. Thank you. If you have any questions, just come here. Thank you. 啊，太累了，反正这一页上不完。OK，就这样，谢谢大家。嗯。